Okay, we're in section 3.1, exponential functions. Our objectives are actually pretty short. This is a short section. We want to simply be able to graph exponential functions, or at least understand the graphs of them, and differentiate exponential functions, which you're going to find is actually pretty simple to do. So the vocabulary is just talking about exponential functions. So while we're talking about some of the differentiation techniques that we've been doing from the past sections, we're going to figure out how to differentiate exponential functions in this section and then logarithmic functions in the next section. And that's because those two functions are inverses, so they kind of go hand in hand. The exponential function derivative is probably my favorite derivative to do, and hopefully you'll understand why when we get there. Okay, so let's go over some basics first of all of the exponential function. We're just going to remember that the exponential function takes the form of f of x equals a to the x. Notice where the variable is. The variable here is the x. That's the independent variable. How do we know that it's the variable? That's where the x is right here. So that's telling you that that's what the function is of. And then, of course, right there in the exponent is the x. The a here actually just represents a constant. So for an exponential function, the base of the function is constant. Very, very important concept here. This right here, this a, is constant. It cannot change in the exponential function. The part that does change is the variable x. Okay, so with a general exponential function, f of x equals a to the x. The y-intercept is at the point 0, 1, so it's 1 unit up on the y-axis. That's where it crosses the y. It's going to pass through the point 1 comma a, and that's because if you plug 1 in for x, you're going to get a to the first power, which is just a. So it would have the point 1a. So for example, if the base a is 3, so you have f of x equals 3 to the x power, then the point would go through the point 1, 3. The horizontal asymptote, I'm going to scroll this down a little bit for you. The horizontal asymptote, which is the horizontal line that this thing is not going, or it's going to approach as it goes off to one side or the other, is y equals 0, and it has no x-intercept. And you can kind of look at the examples that we have down below here. This thing gets really, really, really close to, and as a matter of fact, so close to it, it looks like it becomes the x-axis, but it doesn't. It actually keeps getting infinitely close, but it'll never touch the x-axis, so it has no x-intercept. The domain of an exponential is all real numbers. Okay, any x value that you want to use will work. The range, however, it goes from 0 to infinity. Notice the parentheses around the 0, meaning we are not including the 0. That's because, again, that's where the horizontal asymptote is. This thing will never touch 0. Okay, if a is greater than 1, a being the base. If you have a number which is greater than 1, if you think about this, if we have a number like 2 or 4 or 7 or 10, anything greater than 1, I'm taking a base and I'm raising it to an exponent. What that means is I'm going to take that base and multiply it by itself a certain number of times. Well, you would expect that that number is going to keep getting bigger and bigger and bigger. So if I were to take 2 and raise it to an exponent, like 7, 2 to the 7th power is 2 times 2 times 2, 7 times. It's just going to keep getting bigger. And that's what happens when a is greater than 1. So that's like our exponential growth model, the one on the left-hand side. It will increase from left to right. If a is in between 0 and 1, meaning some kind of a decimal or fraction in between the numbers 0 and 1, cannot be 0, cannot be 1, but in between there, then it's going to be decreasing from left to right, which is an exponential decay model. And again, if you think about it, it will just take a nice easy example. If you take 1/2 and you start multiplying a half times itself, a half times a half times a half times a half, you're going to keep getting smaller and smaller numbers, so you would expect those things to get smaller and smaller as x gets larger and larger. So an example of the exponential growth and decays are given in these graphs, which I've been referring to. The first one is where a is greater than 1. The second one is where a is in between 0 and 1. And you might ask, well, what about if a is less than 0? You can't actually have an exponential function with a negative base. There is no such thing. That's not even a possibility. So if you have a negative base, so you have something in negative, like for example, let's just say you have like negative 5 to the x. That is actually not an exponential function the way that is written. Now, that's not to be confused with if I have negative 5 to the x written like this, not in parentheses. Now this is just the negative of 5 to the x, so almost like it would be like that, because you do exponents before you do multiplication. So the exponent x would actually be done before you multiply it by that negative. If the negative is grouped with the 5, however, that is not actually going to be an exponential function, just to make sure you understand the difference there. Just missed some. Okay, in the particular example on the left, we actually let the base a, we let it equal the number e, which is approximately 2.7182818. And then in the one on the right, we let the base a be 1/2. So you can see the exponential growth and the decay models. So back when you guys took algebra in some form, whether that was back in high school or a college class, you were probably told something about the function y equals e to the x being a special function, an important function, and it really is. It's, again, to me, it's one of the coolest functions as a self-proclaimed math nerd that I am. But let's kind of figure out why that is. I'm not going to go through it extremely in detail, but I'm hoping that you can follow this based on some of what we've done in the past. First of all, we're going to consider the following. We're going to take the limit as h approaches 0 of e to the h minus 1 over h. That will be explained as to why we're doing that in just a second. If you were to take that limit, obviously if you directly substitute 0 into the h's here and here, you would get 1 on top, so you would get 1 minus 1, which is 0, and in the bottom you would get 0. That's going to create a problem. But if you remember, 0 over 0 typically means that you're going to have some kind of a limit. So we can do it numerically, which is what we did in this chart. If we took values of h that get really, really close to 0 from both the left and the right side of 0, and you can see here, this is from the left side, the top arrow is from the right side, it appears that the limit here in between these two things is approaching 1. And if we got closer and closer and closer values of h, you would see that this actually does approach 1. So what we're going to do is we're going to use the fact that that limit approaches the value of 1. So now let's see how that affects things. If we use the limit definition of the derivative, which is kind of the longer way to do it from way back when, before we started learning other shortcuts, because the shortcuts don't work with this. This is not a power rule. It's not a quotient rule or anything like that. If we take the derivative of e to the x, right here, take the derivative. Well, here you can see that this is the difference quotient. This is f of x plus h. This is f of x, and then this is h. So that is the limit of f of x plus h minus f of x over h. Well, what I can do algebraically, and I'm going to write this down here real quick, this piece actually simplifies to e to the x times e to the h. And that's because if you multiply common bases, you add the exponent. So we're really taking that process and going backwards. That's why I can factor, in the next step, I can factor this e to the x out of both terms on top. And what that leaves us with is this e to the h minus 1 over h, because what I can do with that e to the x, I can take it out to the front. And you might think to yourself, wait a minute, that's a function, it's not a constant. But look at the variable. The limit is being evaluated with the variable h. The x part, the e to the x, has nothing to do with h, so actually it can be taken out to the front. And when we take e to the x out to the front, what we get left is this limit that we've already decided was 1. So ultimately what we get is e to the x times 1, which is just e to the x. So what does all that mean? Well, what we just did was we took the derivative of e to the x and got e to the x. How awesome is that? So here we go. To me, that is the coolest derivative, because literally the derivative of e to the x is e to the x. Wonderful. It's going to make things really easy for us to do for the most part. Okay, so let's see how it fits. Let's do a few examples and find dy dx. So on the first one, dy dx. Well, I've got 3 e to the x. 3 itself is a constant, so really I'm just taking the derivative of e to the x, which we already know is e to the x. So the derivative of 3e to the x is just 3 e to the x. Easy enough. Okay, let's look at letter B. Let's put this together with a product rule. So our derivative, dy dx, is going to be the product of x squared and e to the x. So the derivative of the first is 2x times the second one, e to the x, plus the derivative of e to the x is e to the x times the first, x squared. That's it. That's your product rule. We can simplify a little bit there if we really wanted to. We could factor out an e to the x, but there's really no need to do that. And then in part C, we're going to do a quotient rule. So dy dx, the derivative of the top is e to the x times the bottom, x cubed, minus the derivative of the bottom, which is 3x squared, times the top, e to the x, all over the bottom squared, x cubed squared is x to the 6th. Once again, that actually can simplify because technically we can divide an x squared out of everything, but we'll save that for another time. All right, let's put this together now into a chain rule. Notice that what we have here in all of these, your exponent is something other than just x. So what we've done is we've actually replaced the x with another function. So this is a composite function, which means that we have to apply the chain rule. So when we do the dy dx here, for example, in letter A, dy dx, it still starts off the same way. It's just the derivative of e to the x, in this case would be e to the 8x, so it's going to be e to the 8x. But then using the chain rule, I have to multiply it by the derivative of the composite part, which is 8x. Well, the derivative of 8x is 8. So really, I'm just going to rewrite that one. That's 8 e to the 8x. Okay, let's do the same thing with part B. dy dx is going to be, just rewrite the rewrite the exponential, which is e to the negative x squared plus 4x minus 7. But then don't forget to multiply that by the derivative of the exponent itself. The derivative of that exponent looks like it is negative 2x plus 4. And I had to put that in parentheses because that's an entire quantity, which would have to get multiplied times the e. So if you only wrote the 2x part in quantity, then you would be losing the rest of it. You'd be losing the 4. Okay. Let's go ahead and do letter C, which is dy dx equals, again, the first step is always just rewrite it. And then I have to multiply that by the derivative of this square root of x squared minus 3. Well, a square root, remember, is a 1/2 power, so it looks like we're actually going to have a chain within a chain. So let's see how that works. So it's going to be a 1/2 times the inside of the square root, and I have to reduce the power of 1/2 by 1, so that becomes a negative 1/2 power. But then I still have to remember to take the derivative of the inside of the square root because it's another chain rule. So in this case, we're going to have to multiply that by 2x. Okay, that was probably the most complicated one that we have there. And once again, that could be cleaned up a little bit. But again, that's perfectly fine just for taking a derivative. So here is the general rule. The derivative of any exponential, and in this case, we're going to say the derivative of a to the, and we'll call it f of x, we'll call this some kind of a function of x as the exponent, is going to be simply rewrite it a to the f of x times the derivative, and then technically it's times the natural log of the base. We will probably not have to worry about that because in the examples A, B, and C, the base was all e, and the natural log of e is 1. So that typically means that this part right here is going to be 1. If you happen to have a base other than that, this is what you do. So rewrite it times the derivative of the exponent times the natural log of the base. That's it.